Let me get my slides together. And okay, is everybody able to see the slides? Here, let me check back and make sure that's. Oop. Whoop. Sorry, 1 second. Okay, all is good. Okay, all right, just checking. I can't see the I can't see the chat and the slides at the same time. So if anybody wants to interrupt me, Ben, I hope you're able to break in through audio for that. Oh, you're on mute, comrade.
There we go. If you guys want to, if you have questions, please put them in the Q&A. I'll monitor that, and if you don't mind, I'll jump in from time to time.
Go ahead.
Okay, great. I'm gonna hand this back to you, sir.
Okay, thank you all. All right, and hopping over to my screen share now. Okay. All right, so I wanted to talk about containers, but not in the usual sense. Like there's like a million of these, like, oh, what's the internals of Docker like talks. So I'm not going to do that. I'm going to talk about like a little bit more abstract. I'm not a computer scientist. I'm a mathematician, so I like abstractions. I want to understand. I want to take a concept and understand like what does this look like, not in the particular setting that I'm accustomed to, but in like a broader sense. So that's what we're going to do here is understand not Docker containers, but like the wider concept of OS virtualization. So let's talk about what this is. It is effectively when we talk about OS virtualization, the kernel is lying to applications about their environment. So it's going to lie and tell the application that it's got a different host name than it really does. It's going to lie about how much RAM the application might have. So, and this is sort of already a lie that the operating system is already telling us. If you think about like, virtual memory and page swapping and stuff, we already lie to the process about how much memory it has, right? So this is just taking, when we talk about constraining that to a container or to some other kind of process group, it's that same lie, but distorted a little bit. We lie about what libraries are installed. So, this is sort of the lie that really has propelled Docker into the forefront, is that application packaging, right? Being able to get all your dependencies into one slug and ship that somewhere. But those dependencies are not on the host, right? So we're lying to the application in that sense. One of the better lies is lying to the application about whether it's root or not. So if you can tell the application that it's root, say, yeah, you're root, do whatever you want. That's a really great lie, because then the application thinks like, oh yeah, this is my box. I'm in charge. The world revolves around me, but really it's just stuck in its own little container. It doesn't know any better, right? So these are sort of the fundamental lies of OS virtualization. And the reason that we want to lie is because we don't want to have to rewrite our applications to be aware of the truth. That means that the application has to be aware of the virtualization constructs. It's just way easier if the application doesn't know any better, right? So again, this is the kernel specifically, and there's some help from other layers of the OS in some different types of OS virtualization. We'll get into that later, but mostly it is the kernel presenting a fictional version of itself. And processes should not need to know any different. If they do, that's fine, but it's just not as easy. Normally we call this containers, but OS virtualization is a broader concept than containerization. So let's give a brief history of different attempts at this on different platforms. So back in the day, early BSD, Bill Joy, who wrote VI, not Vim, but VI, and then was one of the founders of Sun Microsystems, when he was working at Berkeley on BSD, wanted to be able to do development on new versions of BSD without rebooting all the time. So he created the chroot system call to lie to other processes about their working directory and what the highest point of their directory hierarchy could be. So by lying to the compiler and to the text editor, he could say, and to the linker as well, he could do this development work on the same kernel, but with newer libraries that he could build and control. So that saved him a lot of development complexity. And again, the trick there is to tell the kernel when there are any of the open family of syscalls that they, their arguments need to be preempted, right? Like, well, we've actually got this longer prefix that we need to stick into that argument. It was not originally designed for security, right? This was designed for Bill Joy to be able to get some work done. So, you could just cd ... and pop out of these things. It was not there to contain you. It was there to help you. It was less of a prison cell and more like a cubicle wall, right? So then the next sort of big thing is environment modules. And if any of you have any background in supercomputers, you'll probably gag when you see this because, it's like the bane of your existence. But effectively in Unix, and I think, Wesley, there's some equivalent in Windows, but if not, you can fuss at me afterwards. There's this notion of the LD library path environment variable. So when you start an application, the dynamic loader, so not really part of the kernel, but a user space process that participates in, in laying out your executable in memory, it's looking in this environment variable for dynamic libraries. It'll load the first thing that it finds that matches in that path. So this allows you to sort of mislead the application about what packages are even available on the system, right? Like, we've all struggled with this before. Like, okay, I want to install, one version of this application, but it brings, in that RPM, it's got all these extra dependencies with it, and one of those conflicts with something I've already got installed. Environment modules is there to solve that problem. If you've got an upgraded library, you don't overwrite that library. You put it in a different folder and you prepin that path, the LD library path. Nothing else needs to change. So any existing applications don't need to change as long as you can control this environment variable for new execs of new applications. So environment modules, so again, this LD library path is like baked into most Unices. Environment modules is like a shell facility that sort of automates this. So you can type a command like module load, Python, whatever version, and it will change your running shell environment variables so that when you run Python, it is Python 3.7.6 with appropriate shared libraries, not 3.7.4 or 2.7.8 or whatever, right? And it can do things like handle conflicts. Like you can say, oh, I'm going to load Python, and it'll be like, son, you've already got Python loaded. You can't have two of these running around. So it's got some facilities for that. And it's all controlled in user space. So most of what we're talking about with OS virtualization is to do with syscalls. And we'll talk about that later, but that's the interface between a process and the kernel. But this one is all environment modules are all done in user space. So then the next big advance in this was FreeBSD Jails, and that happened in 2000. And the goal was to take chroots from 1984, but apply this to all OS services. There's a really cool paper, and if you've got any interest in containers, even on Windows, I think, even on non-Unix platforms, this paper, Confining the Omnipotent Roots, by two FreeBSD developers, came out in 2000. It's a really great paper because it distills, for the first time, a lot of these things that we are like, when we think of Docker, like this notion of like packaging and like, automating this whole sub-entity of the OS. They're really distilling and crystallizing that for the first time in that paper. And it's a really exciting paper because they don't know what languages to use. They don't know what words to use yet, So they'll say like, oh, this process is in jail. It's in a jail. We've jailed the process. We sent the process to prison. Well, it's like, they don't know. And they also talk about like, oh, these are basically virtual machines. And now we sort of scold people. Like we say like, oh, well, a container's not a virtual machine. It's a container. But like they didn't have better language at that time. So they just called them virtual machines. But like we would not do that now. Their emphasis was on VPS systems. So in the early 2000s, and those of us that are a little bit older, I'm not quite of this generation, but there were like, in that time, there were these like remote Unix terminals that you could log into from your home computer. So you didn't really have Unix at home. You had whatever system you had at your house, but if you had PuTTY or whatever, you could log into a shared Unix system. That's sort of what jails were really targeted for, was giving everybody their own virtual private Unix server. There is in each process in FreeBSD, there's a data structure called prison, and we'll look at this a little bit later, but that's basically all syscalls. So every time you call into the kernel's going to look at that prison structure and determine, can you do this? And when I do this operation on your behalf, am I going to affect the whole system, or am I just going to affect the other processes in the same jail as you? And again, this gets back to the language feature, right? Like the data structure is called prison, but the concept in the paper is called jails. Like this was sort of half-baked. It was really good, but it was still a little bit half-baked. This prison data structure lives in in the kernel, we have, for every process, we have all this metadata for the process. And so that's where this lives. That's where like your UID is, your GID, your file descriptor table, all those things are in the kernel, because if they were in user space, you could mess with them, right? And for the sake of like you not being able to corrupt your own process space, they have to live in the kernel so that you can't change them from user space. Just like other environment variables, ulimit settings, things like that, this prison structure is inherited by child processes. So if you've got a prison structure associated with your process and you fork, that child gets that same prison structure. And so there's no way for a, you can't just like arbitrarily write to your prison structure. The jails command is the only thing that can create new processes with a specific prison structure. And then only from that point, only inheriting can copy that, but you really can't write to that otherwise. And that's sort of how we preserve the integrity of a jail. The next big thing is Solaris Zones. Their goal at Sun at this time, they looked at the jails paper and they're like, there's a lot of good stuff here, but there's a lot of shortcomings too. So we're going to get it right. In the original jails implementation, they didn't isolate the network stack. Well, so it ends up each jail has its own IP address, which makes sense, but you can't ping, because for those of you that know, ping allows you to write to a raw network socket, so you can like spoof addresses and stuff, and it's like really dangerous to let somebody on your box be able to do that, because they can like, emit traffic that looks like it emanated from you, and that's not very good. So in jails by default you can't ping. Well, gosh, if I don't have ping, I'm like a little bit limited in debugging some things, right? You don't have isolated inter-process communication. So Postgres, for example, connecting a Postgres client to a server relies on Unix System 5 shared memory IPC. Doesn't matter the details, but like there is a inter-process communication vehicle that you can't use in jails because they sort of like didn't have time to finish it. And even in modern FreeBSD, it's like not totally legit that just like works out of the box. There's no resource limits in jails, right? So, there's ulimit in FreeBSD, right? There's ulimit in all Unix, but there's no notion of applying that type of construct to the jail as a whole. So, if ulimit's not set up right for the init process, for the process one of the jail, then anything in the jail can basically eat up an arbitrary amount of RAM, right? So like this isn't, you can do it in FreeBSD, but it's not baked into jails. So that's one of the things that in Solaris they wanted to get right with zones is like, we're going to have all these things. We're going to have a virtual network stack. It's going to have its own IPC. It's going to have resource limits. Also, the coolest thing that they did here, and we'll touch on different ways that this shows up in other operating systems later, their main financial driver, because when this came out in 2004, there was a big rewrite of Solaris at this point. Solaris 9 to 10 was about as different as macOS 9 to 10. So what they wanted to do was to be able to support old Solaris binaries, because they had all these enterprise customers on, how else are they going to get them to upgrade if their binaries don't run? But they've made massive changes to the OS. So you could launch a zone and say, well, we're not going to have the Solaris 10 system calls. We're going to support the Solaris 9 system calls. So you've got a virtual system call table, and then old binaries don't know the difference effectively. So they can run and they think they're interacting with the Solaris 9 kernel. So that's a really neat way to sort of like, they've provided this isolation, but also being able to preserve legacy apps going forward at the same time. Heavy emphasis on running untrusted code. So FreeBSD was sort of like, yeah, we want everybody to have their own virtual private server. but that's for hobbyists, right? So at Sun, they're like, okay, well, we have enterprise systems, and we want to be able to sell people big honking servers, right? Like anybody that was, in the industry in the early 2000s, like Sun sold these gargantuan systems. And for a while, Cray was a part of Sun because their business is, the business of selling single big honking computers had a lot of alignment. And then, Cray got spun back out. Cray's had a bunch of different owners over the years. But the notion of running untrusted code is not just like, okay, yeah, some university student can log in and have like a shell and email account, but like we can have these different departments within our corporation, different divisions within the university running on the same system, maybe even having, software that was developed for us by vendors or software that we're running on behalf of customers run on our same hardware. And we can trust that it cannot escape, this I don't want to say container because they didn't have that word then, but this containment unit, right? This zone. So they really took this notion of running untrusted code, and that is like a first-class concept. Not to say that there haven't been problems over the years, but like it is advertised as a feature of Zones. That is an intentional goal that they wanted to achieve, was being able to run untrusted code. So IBM, right? Everybody else has got one. So IBM's like, we're going to have one. So AIX was once described to me as Unix, but written by aliens. I think that holds for WPARs. This stands for, I left this out, this stands for workload partition. It is like Jails, and again, Jails is part of FreeBSD, so I'm not going to say IBM just lifted all that code, but it was open source code that they could probably look at, right? So it's like Jails, but it's got some zone properties in it. The networking stack is shared by default, so unlike Zones where they've all got their own virtual NICs, but they do have that notion of being able to run legacy apps. So again, for IBM, they're the same thing. They're making big changes to their OS. They want to be able to bring legacy customers along. So the big advantage of WPARs is the same thing, where it's got this virtual system call table where it can lie. Again, all of this is about lying to the process. So it can lie to the process and say, I'm not AIX7, I'm AIX5. Here's all of the system calls that you expect to be able to make. And, they get mapped, or, whatever needs to happen under the hood happens. But the point is that the binary doesn't know the difference. The process doesn't understand that it is in an isolated container. They don't market WPARs as good for running untrusted code. It's IBM, so they're never going to outright say, don't use this. But when you look at this stuff, they sneak in like, well, LPARs are really what you want for isolating untrusted code. We may have time to get to that later, but LPARs are basically, instead of partitioning the operating system, you partition the machine itself. And that's, those of us that are mostly in x86 land, we don't really have any notion of that. But in Power, it's like, yeah, you can partition the machine, run multiple OSs. It's no big deal. Now we're in like familiar territory, right? So 2013, this company called .cloud releases this tool called Docker right before they go bust. But they're not solving the problem that the people were trying to solve in the Jails paper about confining roots. They're focused on application packaging, right? They're not like Zones where they're targeting sysadmins and helping sysadmins be able to break down these, giant boxes for smaller services. They're focused on developers being able to package applications. The Docker registry is a really innovative thing that like these prior constructs don't have and weren't even really going for, right? Like when you build a chroot, you're just making a new directory. When you're building a jail in FreeBSD, there's some like base packages that go in there, but it's like always the current version of FreeBSD base libraries that go in there. This notion that like you might, because like distros is a very Linux thing. These other OSs don't really have distros, right? So with Docker, they're sort of like, okay, you're going to share the kernel. Anything beyond that is up to you, right? And so that sort of gives us this notion of registries where we can like pull fully formed bases out of the sky and just run those. So that's really neat because we don't have to build our prerequisites by hand every time. In Linux, if you're not familiar, the syscall interface is broken into different topic areas, and those are called namespaces. Mount namespaces, control what mount points, network namespaces, help you for all the different things that you would want the the kernel to do for you are broken into different topics, and you can get different namespaces out of each of those. The kicker here is the user namespace. This is what allows you to become root in a container, right? Before, and user namespaces are like, they're relatively new in enterprise Linux, because enterprise Linux is behind the upstream kernel by a few years. Usually it takes a while for some of these newer features to trickle down. So, I worked on the Titan supercomputer, which came up in 2011. So it had, it was running a version of SUSE Linux that came out probably in like 2008 or 9. So it didn't have user namespaces, and that was like a big kicker for me. But somebody speaking up.
Yeah, so we got a
Hey,
from a mystery guest. Did I miss LXC? Where was that?
I'm not talking about LXC. Because that's a good question. So, and I wasn't really planning on touching on this. With Linux, there's like a million different containerization tools, right? And part of that is because some of these tools exist in the kernel, but the notion of a container does not exist in the kernel. So the container is about namespaces and C groups, but it's up to higher level tooling to sort of assemble that into something. LXC is this sort of like minimalist container system, and Docker can build on that and use part of that and then re-implements part of it on its own. There are tons of other container systems in Linux. So there was one that's really popular in supercomputers called Singularity. That's popular because it's, instead of using layered file systems like Docker does, it uses what's effectively a giant tarball for the system image. And that's just like easier for supercomputers to deal with for a lot of reasons. So I am glossing over all of that and sort of equating Linux containers with Docker for the sake of this talk. Those of you who know better, just enjoy the non-Linux portions of this. But everything that Docker does, these other systems aim to do parts of that, but with some kind of they'll have some special goal that separates them from Docker. So the way I view it is a lot of the other containerization systems on Linux see themselves as an answer to something that Docker is not doing well. But if you disagree with that, hit me. I'll be here afterwards. I know that's a little bit of a contentious point to gloss over that, but I'm doing it. So okay, Windows containers. So 2018, I think, right, Wesley, is when Microsoft says, okay, we have to get with the program. So there's a bunch of different, just like Linux, there's a bunch of different containerization tools on Windows. The one that I think is most interesting is this notion of Windows containers on Windows. So this is the most similar to FreeBSD Jails or any form of containers on Linux, where it's like the application just sees a limited version of the OS kernel. What's neat about these that we don't, those of us in the open source community don't really deal with, well, there's licensed stuff in sort of these base layers, right? Like there's like Microsoft provided libraries. So we can't just like throw that on Docker Hub and share it with each other, right? You have to pull this stuff from Azure. That's how they enforce licensing on this. And then there's some, like, if you look at Microsoft's documentation, they're like, well, if you've got an air gap site, there's like a different way to do it, but it's not like, I didn't dig too much. This is not my bag, but I thought, to me, this notion that like, oh yeah, of course we have to provide proprietary software in a Windows container. That's just, it's something that you don't normally, I say normally for those of us that work mostly in the open source world, we don't normally see this. So there's that. There's also, the question, I'm always interested in this, are this platform's containers good for protect, are they designed for convenience or are they designed for security? Microsoft doesn't answer that question outright, but they do put a blurb in the Windows containers documentation. They say, Hyper-V isolation is useful for multi-tenant scenarios with requirements for hosting untrusted code. What they're basically saying is that this normal process level isolation, what we've been talking about so far as OS virtualization, isn't really what you want for untrusted code. So for untrusted code, they want you to use their virtual machine solution, Hyper-V, and fire up a mini VM and then run a single container in that, just as like an extra layer to make sure that nothing busts out, right? And so that's fine. They're being transparent about it, but it's like, I find that particular problem really interesting because FreeBSD and Solaris were like, we're going to nail this. And everybody else is like, oh, it's a hard problem. I don't know if we're really going to do that. And is it a hard problem? Is it an impossible problem? Are FreeBSD and Solaris being too bold? I don't know. But I just think it's interesting that there is a lot of disagreement about whether we actually can do this safely with just the OS kernel, or whether we need this additional, isolation layer of hardware virtualization. There's another thing that you probably heard of called the Windows subsystem for Linux. That Microsoft doesn't really advertise that as a container. That's more of like less a Windows Server thing and more a Windows desktop thing for developers. The version 1 of that is an example of OS virtualization. Microsoft provides this fake Linux system call table. So Linux binaries that have been compiled with GCC and compiled for Red Hat, you can pick them up and take them to a Windows machine that's got WSL1 and run it with no hardware emulation, no Linux kernel presence. All of those system calls are intercepted by Windows and mapped to something that Windows can do. Now that ended up being slow. So Microsoft sort of backed away from that, and WSL version 2 does use a virtual machine, just because when we do translation from one Unix to another, from version 9 of Solaris to version 10 of Solaris, maybe that's not so different. But translating from Linux to Windows, that's pretty different. So it ended up being sort of slow. So to talk more deeply about this, I know for those of you that have computer science degrees, maybe it's been a minute since your last operating systems class. I never had one, so it's been infinitely far in the past since mine. So we'll revisit a bit of theory about how processes and kernels interact, just real quick. Okay, mostly a thread of control will stay in the process, or will stay in user space in your code for math or manipulating data structures. So if you're doing if statements, if you're sorting something, anything that's not I/O or querying the OS, the thread stays in the code for your application. It will go to the kernel for any I/O, networking, things like that, or any questions that it may have, like what's my host name? What user am I right now? Those are things that only the kernel can answer. And when you ask the kernel for that, it's software, right? It doesn't have any ethical obligation to tell you the truth. It has a practical obligation to be consistent, to keep your application from crashing or getting confused. But if the kernel decides to lie to you at that juncture, that's up to the kernel, right? So if the kernel wants to tell you that you live in a tiny little world all by yourself and you are root, then it's okay for you to believe that, because the only other recipient of that conversation is the kernel, which is enforcing this lie. So very, very roughly, a thread will go from the process from user space to the kernel at syscalls. And in that sense, we can think of the kernel like a giant shared library, right? We're making these syscalls, and then we hop into the shared library. And then when we're done with those, we hop back. No big deal. The actual details are very, very different between not just operating systems, but CPU platforms. And if you try to describe it like this in a proper operating systems course, they would tell you to leave. So again, the way we issue a syscall on the machine, and this is with the heavy x86 bias. I don't actually know how to do it on other platforms. There's every system call, every different call that you want to make to the kernel's got a different ID. You put that, there's a special register, and you put that number of that system call in that register. Any arguments you place to the syscall, you put those on the stack. And then there's a special instruction in NASM assembly, it's just called syscall, and that tells the CPU, hey, I'm done for the moment. Hand yourself back to the kernel, because I'm done with you for the time being. So, for example, we want to change our working directory to a directory called Fiji. That is cheater is a Linux, it's a Unix system call. So there's a system call number for that. The directory that's a string, so we can place a pointer to that string on the stack and then call system call, and then the kernel is going to say, okay, I know that the this process wants to be able to change directory. I'm going to read this string out of memory, figure out if this directory is visible to this process, given its current constraints, if it has permissions to change directory there. And if so, then I will change that process's current directory, which is just information that I, the kernel, have about that process to Fiji. So that's how cheater is done. And everything else is pretty similar. So just to show this in a little more detail, that little red circle, that's your thread of execution. It goes from the process to the kernel and back. We say the CPU, and again, this is x86. Well, this is like MIPS. This is like a child reading, a computer architecture book. So probably real CPUs, it's more complicated. When it's running the process, it's in normal mode. There's this special thing called monitor mode that the kernel runs in, and that allows the kernel to access raw memory instead of just virtual memory pages. And because it can do that, that's how the kernel is able to manipulate itself. But the processes only ever use virtual memory. So that's what prevents them from being able to write to the kernel.
So we do have a question here, actually.
Yeah. Go ahead.
So what does hardware virtualization in terms of security that doesn't exist in containers? Aren't they all just processes on some underlying OS?
Yeah, that's a great question. So hardware virtualization provides this protection of I can't write to arbitrary memory locations is enforced by hardware itself, right? So when we talk about hardware virtualization on modern platforms that provide hardware support for this, the CPU actually participates. So when you have a virtual machine, you tell the operating system, when it launches a virtual machine, it says to the CPU, hey, I'm the real monitor here, but when this guy runs, let him think he's monitor. And if he tells you to do something about this other virtual memory, as long as it's within these parameters that I'm telling you ahead of time, go ahead and let him do it. So it's like a delegation. In x86, they talk about things called rings. So there's ring 0 and then ring -1. So these different rings are where the processor has different rights to things. And what you can do with virtualization is you give the VM a synthetic ring 0. So again, it's very similar. It's a lie that the hardware is telling to the virtual machine rather than a lie that the operating system is telling to the process. It's the same thing, but here's where the additional security comes from is you've got hardware backing you. So Intel knows what a virtual machine is, and they've provided extra instructions to make that safer. And there's also, it's a smaller interface between, I don't have to know anything about the application you're running. If you're running a virtual machine, I've got to handle disk for you and network for you and make sure that you get access to the CPU every now and again. That's pretty small, right? I mean, there's obviously more to it than that, but the responsibilities of the hypervisor OS are much smaller than the responsibilities, and that interface is much smaller than the interface between a kernel and a process. So it's safer, some people think, in the sense that there's just less to check and less that can go wrong. I think that claim is up for debate. But it is easier to say if I've got 3 guarantees to you versus 300, it's easier for me to make sure that I can meet those 3, right? I think on the face of it, it seems a lot easier to make sure you can protect that. But deep down, I think it's hard to say which one's safer. Okay, kernel stores information about each process. Who am I? Where am I? Who are my related processes? If it were simple, it would have a container ID with it, but that's not really what's going on. And again, this is located in kernel memory, so it's only writable in monitor mode, right? Malicious or buggy processes cannot write to that. Now, I figured people would say, what about Spectre and Meltdown? Those are, just as a reminder, those are for reading protected memory. Writing to kernel memory is not part of that exploit. I'm not aware of a thing that lets you do that, but if you know, hit me up after the fact, because I would love to know all about it. Okay, so very quickly, we're going to look at some implementation details of different types of OS virtualization. We'll start real simple. Chroot jails. This is what the OpenBSD people are doing. Again, chroot is just going to modify in the kernel what the root directory is for a certain process. Any file system related syscall is going to get checked against that hypothetical root to make sure that that syscall is legitimate within the chroot. OpenBSD has this thing, that by itself, that chroot by itself really isn't enough to pull all this off. So OpenBSD introduces this concept of pledges. If you are a Linux person, you might know about capabilities. Pledges is like the reverse of capabilities. You opt into a pledge, then if you say, I pledge not to make these system calls ever again, and you do, I got this on a later slide, I guess. If you say, I'm not going to call any IO system calls, and you do, the kernel will just kill your process. OpenBSD is a big fan of like, well, if it's wrong, we should stop it immediately. So that's not cool for like application stability. They don't care. They're more interested in correctness. So network access within chroots is protected by routing domains, but they're not coupled. So it's a different concept. You can put the two together, but again, that relies on user space software to sort of marry those two concepts. And again, we get a lot of this when Linux network namespaces, you get like a separate view at IP tables. And routing domains, that's all it is. You don't have a separate network card on top of that. Okay, yeah, play a similar reverse. Yeah, you promised that you won't make a certain type of, I already put this on there. Okay, sorry. Pledges are inherited by a child process. So that's what gives this the notion of like a container, is if you start in a init process in a chroot with a certain pledge constraint, then all of its children will not be able to escape that. Because pledges always reduce the syscall interface. They say like, okay, once you've said you're not going to make these certain types of system calls, you and your children are limited to this smaller and smaller view of the container's capabilities. But again, there's no resource management baked into this. It's a very manual construction. If you want to put stuff in there, you've got to look up all the requisite shared libraries and put them in there yourself. There is no Docker build for OpenBSD chroot. There should be. There's no access to DNS, so you got to put in your resolve.conf by yourself. A lot of times what people do is they'll make the chroot, and then from out of there, they will link in important stuff with hard links so that it doesn't take up any extra space. One thing that's cool about it, because there's not much, it is easy to understand and audit. And that's what the OpenBSD people like about it. They're all about like, we want to audit the code. So they end up having a much smaller, simpler OS that is far less capable because everything about it is audited. So somebody's like, oh, I want to do such and such a feature. They're like, well, we can't audit it. It's too big. We're not going to take it. Doesn't matter how useful it is. Doesn't matter how cool it is. Really doesn't matter if it would improve security. If they can't audit it, they're not going to take it. So that's right. That's their bag. Okay. FreeBSD Jails. Every process has a prison data structure associated with it. Like I said earlier, you can tell the half-bakedness here, because why is it called jail on the outside, but it's called prison on the inside? Like, those are different things, whatever. Prison structs are inherited by subprocesses. You can't clone a prison struct. So you can start a new jail and that creates a prison struct, but there's no way to like make another one with those same contents. There's no way to like join into an existing jail. And then once that prison struct is created, the chroot is like the final step in jail creation. So the prison struct controls all of the OS facilities that you call, except for the file system related ones, and those are delegated to chroot. So that's how jail sort of like really takes chroot and builds strictly on top of it. The default tooling, will build you something that's got procfs, and it will put the requisite libs in it. So it's sort of like having Docker, but with like, there's only one base layer that you can customize the base layer if you want to use a different base layer, but like by default, there's just like a base Docker layer, and any new containers you spin up always have that. So it's a much more limited, this is for system administrators to make a bunch of the same jail, not for developers to make a bunch of different jails. Here's the jail structure, and this is the only code that I really want to look at, because jails is the only implementation that's simple enough to really go over in this fashion. Zones and namespaces are like way more complicated. So right there in this structure, there's the chroot that you've set up for this jail, right? So that's pretty straightforward. These two fields show the host name and the IP that you've set aside for the jail. So again, every jail gets one IP address. Well, if you think about it, like a real Unix system might have a bunch of IP addresses, right? And it definitely, if it's a public-facing system, has at least two. There's 127.0.0.1 for loopback, and then there's the public-facing IP address. Jails don't have that. There's just one IP address, and if you are a process in a jail and you bind to the loopback address, the kernel sees that and says, okay, they meant to bind to the public one that was assigned. So I'm just going to open that traffic up to this public address. So if your host firewall doesn't prevent that, then errant processes that normally mean to communicate with each other over local TCP loopback will just expose that out to the internet. So that's like, again, jails, this came out of academia. It's awesome for what it is, but like there's some really serious foot guns in this thing. The Linux API, FreeBSD has the capability with, again, the same, it's this virtual system call trick. And if we've got time, we'll talk about that in a minute. But because different versions of Linux have different APIs, you can start a jail and you can say like, well, I actually want this jail to be able to emulate this version of the Linux kernel. And so Linux if you've got a Linux glibc and all your requisite libraries, you can run a small Linux environment in a jail. You'd think you could just launch a Docker container in a jail, but there's not enough user space tooling for that. And then the last thing here is this ref count. The way we know for a jail to go away is every process that inherits a jail, this ref count's going to increment. And every time a process that is part of that jail exits, that ref count's going to decrement. So when the kernel, again, this structure lives in the kernel. When that process goes to 0, the kernel knows the jail is over. So it can hand that IP address back. It can any other resources that it knows are associated with this jail, it can let those go. So that's cool. Most of the syscalls check that prison structure. So this is one thing, again, I talk about FreeBSD jails not because I'm like, oh, y'all need to go use them. They are the simplest to understand that does anything more than Chroot does. So there's good balance between like they can do a lot of things, but they're still easy to understand. The big exception is shared memory. And again, I said earlier, like you can't in a jail run Postgres without turning some stuff on that basically makes it unsafe. It allows some vulnerabilities. One thing that really sucks about this, the kernel scheduler doesn't know about this prison struct. So that's why I said earlier, like most of the stuff in the kernel knows about it, but not everything. So you can't use jails by themselves for resource management. They don't have an analog of Linux C groups. So that sort of stinks. Again, each jail has a single IP. Okay, I talked about this. Sorry. I wrote a lot of these slides today, so if I'm talking all over the place, that's why. This local TCP, you can't do it because the jail will just be like, well, loopback, public, same thing. So again, jails are cool, but they're also sort of dangerous if you don't know what you're doing. The host has to make sure that you route correctly, and again, no raw sockets, so you can't ping from within a jail. Ridiculous. So Solaris, so people at Sun Microsystems are like, okay, we're going to do this right. We're going to add resource management. So we're going to say like, you can't use more than a certain amount of RAM. You have CPU share limits. We're going to provide isolated IPC. Each zone gets its own virtual network card. So this starts to sound more mature, right? This is more like what we would expect out of a hypervisor. It gets an independent TCP stack. So that means you can ping and you can do whatever you want to your heart's content. You can't then turn around and like spoof traffic for your neighbor. So that makes it safe for people who don't trust each other on the same machine to be able to have root access over their network. Solaris has this thing, and it's had it before, Solaris 10, called Crossbow, and it's like a virtual networking layer. It has got the same type of features that Open vSwitch provides on Linux. Namespaces, I'm not a big fan, right? This is like, I just think they're more complicated than they have to be. So the Linux syscall interface, most of it is broken into different topic areas called namespaces. Mount namespace controls which mount points a process can see. UTS, Unix time sharing system, controls the host name. Why is that its own namespace? I don't get it. IPC, so if you want to be able to use any kind of shared memory or anything with another process, You've got to be in the same IPC namespace. PID namespaces are cool. You can enter those and become PID1 inside. Maybe you're PID 4082 on the outside. It doesn't matter, but within the PID namespace, you're PID1. So that's neat, right? And so that sort of is what gives us that like isolation when we run PS or top or whatever. Network namespaces. Which virtual NICs does the process see? Where can it send traffic? And then the user namespace, and this is really what seals the deal. This is what allows us to be some nondescript user on the host, but be root inside this namespace. So that all sounds good. What in the world's wrong with that? None of those have anything to do with each other. So you can become one. You can become a part of one namespace without necessarily becoming a part of all namespaces. They're nestable, so you can have like a mount namespace within a network namespace, and it's like some people say that's a feature. I think this is a byproduct of the way that Linux tried to evolve this, whereas FreeBSD and to a greater extent AIX and Solaris said, okay, this is a moonshot. This is one single serious engineering effort. We're going to start from not having it, and we're going to end up with having all of it. So that evolutionary design meant we got bits and pieces at different times, and then they the kernel people are like, it's up to user space to unify them. And again, right, like we have to rely on something at the user space level to get all those abstractions right. And this makes sense because Linux is just a kernel. It's not a whole OS, right? Right? Do you see what I mean, right? So like if we want a unified system, this is where like people think like Stallman's a little bit obnoxious, but it really does drive home the point. Like GNU Linux was supposed to be a unified system. All these distros that we have are like everybody's different attempt to make something unified out of Linux. But like without that, we have this sort of mismatch between what the kernel can do ergonomically and what user space tools let you as an admin or a developer do ergonomically. So again, and I'm not just trying to nitpick here, this has really serious implications. Tracing tools, BPF trace doesn't like know what a container is, right? Because the kernel doesn't know what a container is. It's very difficult because the stuff is all over the place in the kernel. It's happened over, many, many years. It's very difficult to say, well, I'm just going to take namespaces and audit that for correctness. Well, you can't really like reach into the kernel and grab the namespaces stuff and pull it out and look at it. It's all over the place. So it's very difficult to make sure that there's like no subtle bugs in that. So untrusted workloads. Here's my opinion there. If the Linux kernel were safe for untrusted workloads, you would see somebody offering bare metal containers on Linux the way you see people offering bare metal Solaris Zones and bare metal FreeBSD Jails. What happens, and I wish Andy was here because I came up with the phrase Andy's web services. A lot of what they do in their serverless stuff, they're actually wrapped in tiny virtual machines because they want that hardware virtualization as a buffer against what, in my opinion, Amazon sees as having a little doubt about the Linux kernel's capability to do this on its own. So this next section I'm going to breeze through because we're running short on time, but this is sort of out of our normal container mind space, but in other areas where we take, we let the kernel using the syscall interface lie to processes about what's happening. This notion of dynamic recompilation with emulators, Apple has changed their CPU a few times, right? So when they first went from Motorola to IBM, they had a bunch of legacy applications that were compiled for Motorola 68K. They came out with this emulator for dynamic recompilation. They shipped it as part of classic Mac OS. You could run these 68K apps. I mean, these are artists and people running Photoshop. They don't know any better, right? The OS will just tell the application like, yeah, you're on a 68K, no big deal. Those syscalls were translated dynamically from 68K to PowerPC, shipped to the PowerPC host kernel that didn't know it was interfacing with a 68K application. How cool is that? Rosetta. So Apple did this again when they switched from PowerPC to x86 around middle 2000s. Same trick. They had an emulator that dynamically translates PowerPC to x86. The emulator lies to the app about what CPU it's running on, and then the kernel doesn't need to know any better. That's not exactly true. The kernel actually, does some shenanigans to make this fast. Apple, again, if you paid attention to the news, Apple's ditching Intel and they're going to their own ARM thing, right? If you look at Apple's docs, they've decided to continue the Rosetta name because they're going to do this trick. So it's going to be the third time in as many decades that Apple has done this, this emulation trick to allow their legacy applications to same OS but shift CPU. QEMU does the same thing. You can do this for Linux. It's totally emulated in user space, so it doesn't get special accommodations from the kernel. Where I worked at Oak Ridge, some people, there was a time where people wanted to be able to build PowerPC Docker images, but we didn't have PowerPC available for them to do that, so they had to do that on Linux. If you hate yourself, you too can do that. The last thing I want to touch on is the classic Mac OS environment. Again, Apple, we think about containers, it's it's, Docker and applications and stuff, but this is where OS virtualization is really much broader than that. When they moved from Mac OS 9, which was not Unix, to Mac OS 10, which is, they had all these applications that people wanted to be able to bring over. So, this was a cool thing they did where I want to be able to run Mac OS 9 apps and Mac OS 10. The kernels were so different, the operating systems as a whole were so different that they developed a sidecar process that just kept track of windowing state and the types of things that Mac OS 9 did that Mac OS 10's kernel really didn't know what to do. So any syscalls that the Unix kernel, the XNU is what they call it, but any system calls that kernel knew how to intercept it would, and anything that it didn't know about, it would just ship off to this fake Mac OS 9 process. So again, OS 10 is just lying to the apps. It's yeah, you're on Mac OS 9, whatever. And this actually helped because, when OS 10 came out, there was no Photoshop for it, right? A lot of their killer applications were these, for this historic operating system. So they had to come up with some way to support this forward. We don't have time for this. FreeBSD can do Linux binary compatibility because you need that. Everybody, Linux is the de facto. This is why Microsoft has, Linux containers on Windows and the Windows subsystem for Linux. Whether you like Linux or not, it's just so much software is written for it. You have to be able to support it. So this sort of goes over how FreeBSD supports it. Illumos is, what we call Solaris these days. Same thing. So again, we take this notion of being able to put in this fake virtual call table, and that's what processes hit. And those are sort of translated opaquely to the process by the real kernel. Blah, blah, blah. There's one Illumos distro that has a fake Docker engine. The coolest thing about that is you can build Docker on your Mac laptop with Docker for Mac or whatever, which is running in Linux VM behind the scenes, push that to Solaris and then run it in production on Solaris. And the whole time your application thinks it's just running on Linux. So that's a whole bunch of really well orchestrated lies happening at once. I think that's impressive. The Windows subsystem for Linux, because I'm running out of time, same thing, virtual system call table. That turned out to be too slow. Whoops. Sorry. Because that turned out to be too slow, Windows WSL2 now runs in a VM. So there used to be not a Linux kernel. They added one, and they added hardware virtualization to make it faster because Windows and Linux are so different, they just couldn't do that quickly. And you can run Docker on mainframes, same thing. Any questions?
Turn my mic on. There we go. My mic is on. All right. How do container orchestration like Swarm or Mesos handle all this low-level kernel stuff across computers?
So that's interesting. I don't know. I purposefully left that out because I was really focused on how the syscall interface gives us this opportunity to construct these lies. Now, I think that the orchestration stuff doesn't happen at that level, right? I think that's all done in user space. I don't know that for a fact. I will say one thing that I actually, in doing this research, you can run AIX in IBM's cloud. So I paid, $50 for this stinking AIX machine, little bitty, 1 gig of RAM, 1 CPU core. Most of that's the AIX license to run some WPARs. AIX has the ability to evacuate WPARs between machines. So if you define the same WPARs on 2 different AIX hosts, there's some, and I don't know the implementation, but if one of the hosts goes down in a graceful way, it has time to evacuate those containers over to another host. So there's like container level failover on AIX. Is that what you want? Do you want to run AIX? Like, surely Kubernetes can get you something just as good. But I thought it was neat that it is, the thing to me that's neat about that is it's baked into the operating system, right? And I think that's cool. Whereas in the GNU Linux environment, less is baked into the kernel and more relies on things up the stack. So you end up with like, things up the stack are like, I don't know. It's just it's a value judgment. It's not like it's less good to do it that way. I like the neatness of everything being unified and sort of done by the same set of people and having the same feel, same motif, documentation's in the same place. These different components are aware of each other, but that doesn't suit everybody's needs. So, but yeah, different tools probably have different level of inspection into this, but I don't know if anything. People who are more experienced will be able to answer that question better. I've not done enough like running containers across systems to be able to say with any authority what those do at like a kernel level. Like, where do they participate in these lies? I don't know. Anything else? Okay, well, it's 8 o'clock. We need to get to drinking. So thank you for coming. And in case I don't see you, good afternoon, good evening.
Muted. I put the link in the after. I put the link in there for the after party. Join us there. That's what I was trying to say, but I was muted. But thank you, everyone. All right.
Thank you so much.
Wait a minute. We got another couple of questions. Oh,
okay. I'm here.
No, we don't actually. Mystery guest was, why am I the only one asking questions?
Okay. I'll be at the after party.
Oh, wait, Andy Cowell.
Andy.
His hand is raised. I'm going to give him the floor.
Yes, please.
Andy, would you like to join us?
On it.
All right.
I wore my Andy's Web Services shirt just for you, man.
Yeah, I'll get you one.
Plenty of time for your abuse.
Okay, cool. Good. Yeah, I came up with that joke just for you. I wanted you to hear it. Okay. Well, if there's no questions, I'm going to hop in the after party.
All right. Thank you, guys. Thank you, Robert. Everyone, take care.